3 hours ago, meteorological stations across the Western Pacific detected something that should not be possible. A Category 5 typhoon, already at the theoretical ceiling of atmospheric violence, began intensifying. Not slowing, not stabilizing, accelerating. In the past 6 hours, central pressure has dropped 45 millibars, a rate of change that violates every model we have built to understand how storms behave. Wind speeds climbed from 250 to 320 kilometers per hour. Computer projections show that if this acceleration continues, Sinlaku could become the first storm in recorded history to strike United States territory with winds exceeding 350 kilometers per hour. At that threshold, we are no longer discussing damage, we are discussing total structural disintegration. And right now, at this exact moment, the storm is still gaining strength. Before starting the video, be sure to subscribe, like and write in the comments from where and at what time you are watching us. Let me give you a number that should make every atmospheric physicist on this planet stop what they are doing. 45 millibars. That is how much Sinlaku's central pressure dropped in 6 hours. For context, a typical Category 5 typhoon might drop 10 to 15 millibars over the same period before hitting natural atmospheric resistance and plateauing. 45 millibars is not an intensification rate. It is an atmospheric collapse occurring inside a storm system that was already at maximum theoretical intensity. The meteorological term for what Sinlaku is doing is rapid intensification, but that phrase was designed to describe storms moving from Category 2 to Category 4, not storms that have already reached the ceiling and then decided to ignore it. Every atmospheric model we have, every framework built from decades of satellite data and hurricane physics, tells us that once a storm reaches Category 5 status, natural braking mechanisms engage. The storm begins churning its own fuel supply. Wind shear increases, the ocean beneath starts cooling from the turbulence. These are not theoretical limits. They are physical laws observed in every major storm system for as long as we have had instruments sensitive enough to measure them. Sinlaku is not obeying those laws. At 0300 hours UTC, wind speeds were measured at 250 kilometers per hour. 6 hours later, at 0900 hours, that number was 320 kilometers per hour. The acceleration is not random, it is not chaotic. It is happening in discrete jumps, synchronized pulses of intensification that occur with disturbing regularity. Every 6 hours, the pressure drops. Every 6 hours, the wind speed climbs. Every 6 hours, the storm becomes something it should not be capable of becoming. Computer models attempting to project Sinlaku's landfall intensity are producing results that scientists are privately calling impossible. 350 kilometers per hour, sustained winds at coastal impact. To understand what that means, consider this. The most violent tornado ever recorded, the El Reno storm that rewrote our understanding of atmospheric extremes, produced winds estimated at 480 kilometers per hour over a narrow path for a few minutes. Sinlaku, if these projections hold, would deliver 350 km per hour winds across a front spanning hundreds of kilometers, sustained not for minutes but for hours. Every structure within 50 kilometers of the eye wall would experience forces that no building code on Earth was designed to withstand, not damage, disintegration. The question hanging over every monitoring station right now is simple and terrifying. What is sustaining this storm against every natural mechanism that should be stopping it? Open the database of every Category 5 storm recorded in the satellite era. Search for any system that continued intensifying after reaching maximum classification. You will find scattered cases of brief fluctuations, 12-hour periods where a storm held its peak before the inevitable decline began. You will not find a single confirmed instance of a Category 5 storm accelerating beyond its initial peak for multiple consecutive measurement cycles while maintaining structural coherence. Until now. The atmospheric physics preventing this scenario are well understood. When a tropical cyclone reaches extreme intensity, it creates its own worst enemy. The massive wind circulation stirs the ocean beneath it, pulling cooler water from depth to the surface. That cooler water cuts off the heat engine driving the storm. Simultaneously, the extreme rotation generates turbulence that disrupts the organized vertical structure required for intensification. The storm, in effect, begins cannibalizing its own fuel supply. This is not a theory. This is observed reality in every major hurricane and typhoon we have studied. Sinlaku is somehow bypassing this self-limiting cycle. Ocean buoy data from directly beneath the storm's path shows something that should not be appearing in those readings. The sea surface temperature is not dropping. After 18 hours of a Category 5 system churning directly overhead, the water temperature has remained constant, in some measurement zones actually increasing by 0.3 degrees Celsius. The subsurface temperature profile shows no sign of the normal cold water upwelling that we see in every other major storm system. The ocean is not cooling. The fuel supply is not being interrupted. Atmospheric physicists reviewing this data have noted in internal communications not intended for public release that the thermal stability beneath Sinlaku resembles patterns seen in laboratory simulations of artificially sustained convection systems. One researcher described it as looking less like a natural storm and more like an experiment in controlled atmospheric manipulation. That comment was never repeated in official channels. Review the historical record more carefully. 3 storms over the past decade showed brief periods, 6 to 12 hours, where intensification continued past Category 5 thresholds before suddenly collapsing. Typhoon Haiyan in 2013, briefly. Super Typhoon Meranti in 2016 for approximately 8 hours. Hurricane Patricia in 2015, which produced the lowest pressure ever recorded in the Western Hemisphere before rapidly weakening. Each of these events was treated as a statistical outlier, a rare confluence of favorable conditions that briefly allowed nature to exceed its normal limits. Look at where those storms occurred. Pull up the bathymetric charts, showing ocean floor topography beneath each track. Notice the pattern. Each of those 3 anomalous intensification events occurred over deep ocean geological features, subduction zones, volcanic island arcs, regions where the ocean floor is tectonically active, where deep earth heat flux is measurably higher than surrounding areas. 3 events, 3 different ocean basins, same geological correlation. And now Sinlaku, tracking directly over the Mariana Trench system, showing the same impossible acceleration, except this time it is not stopping after 12 hours. This time it has sustained for 18 hours and counting, with no sign of the natural collapse that terminated those previous events. The database cannot explain this. The physics we thought we understood cannot account for what the instruments are recording. Sinlaku is not behaving like weather. It is behaving like something weather does not do on its own. Approximately 36 hours ago, before Sinlaku reached Category 5, before the public weather services began issuing the upgraded warnings that are now dominating news coverage, a different set of instruments detected something. Not meteorological satellites, not the civilian weather monitoring network, deep space observation platforms, systems designed to monitor solar radiation and cosmic ray flux, registered electromagnetic anomalies emanating from the coordinates where Sinlaku was beginning its intensification sequence. The readings were brief, 60 to 90 seconds of elevated electromagnetic activity in frequency ranges that atmospheric phenomena do not naturally produce. The signature appeared once, then again 6 hours later, then again 6 hours after that. Each burst coincided precisely with one of Sinlaku's accelerated intensification pulses. Atmospheric lightning produces electromagnetic signatures, but in entirely different frequency bands and with chaotic timing patterns. What the satellites detected was rhythmic, repeating at exact intervals, and occupying a portion of the electromagnetic spectrum associated with deep crustal processes, not surface weather. Scientists who monitor space weather phenomena, the interactions between solar wind and Earth's magnetic field, have access to these readings. In private communications between research facilities, the term being used is coupled system discharge. The hypothesis, not stated in any official publication, is that under specific conditions, electromagnetic energy from deep geological structures can propagate upward through seawater and into the lower atmosphere, where it interacts with existing storm systems in ways we have never observed outside of laboratory plasma physics experiments. This is not fringe speculation. The physics of electromagnetic coupling between Earth's interior and its atmosphere are well established in geophysical research. What is unprecedented is seeing it occur at a scale and intensity that appears to be sustaining a Category 5 typhoon beyond all natural limits. Every 6 hours, the electromagnetic pulse appears. Every 6 hours, Sinlaku intensifies. The correlation is mathematically significant beyond any reasonable threshold for coincidence. Request the raw satellite data. You cannot. It exists within classified observation networks that share findings with civilian meteorological agencies only after filtration and interpretation. The electromagnetic readings were noted in internal research channels and then quietly archived without official commentary. Weather forecasts make no mention of electromagnetic anomalies because weather forecasts are generated from atmospheric models that do not include variables for crustal energy discharge. The models cannot see what they were not designed to measure. 3 previous storms showed this same electromagnetic signature: brief pulses, 6-hour intervals, coinciding with impossible intensification before the storms rapidly weakened. Researchers who noted the pattern submitted findings to peer-reviewed journals. The papers were accepted, published in specialized geophysics publications with limited circulation, and never referenced in mainstream meteorological literature. The communities studying weather and the communities studying deep Earth processes do not speak the same language. They do not read each other's publications. They do not attend the same conferences. And so the pattern, documented in one field and invisible to the other, was never integrated into atmospheric forecasting frameworks. Until now. Until Sinlaku demonstrated that the pattern was not an anomaly, it was a preview. Go deeper. Below the waves, below the thermocline, where surface temperature monitoring instruments typically operate, oceanographic buoys positioned along Sinlaku's track recorded thermal profiles that make no sense within conventional ocean circulation models. At depths of 300 to 500 meters, where seasonal warming should not penetrate, water temperatures measured 4 to 6 degrees Celsius above baseline, not scattered hotspots, a continuous thermal corridor extending for more than 800 kilometers along the precise path Sinlaku has been following. Ocean heat content at depth is the true fuel reservoir for major storms. Surface warming alone cannot sustain Category 5 intensity for extended periods. The storm needs deep, warm water, what oceanographers call high ocean heat content, to maintain its power when surface turbulence would normally cool the upper layers. What the deep buoys are showing is not just high heat content, it is anomalous heat distribution that appears to be concentrating along a linear corridor, as if something beneath the ocean floor is channeling thermal energy into a narrow pathway that the storm is following with impossible precision. Pull the bathymetric charts for this region, overlay the thermal anomaly data, notice where the heat corridor aligns. Directly above the Mariana Trench system, the deepest subduction zone on Earth, where the Pacific Plate descends into the mantle at angles and depths that produce the most extreme geological conditions anywhere on the planet. The trench is not a passive geological feature. It is an active boundary where tectonic forces generate heat through friction, where volcanic processes release geothermal energy into the surrounding ocean, where the physics of plate tectonics operate at scales and intensities that dwarf any human reference point. Geothermal heat flux from deep ocean spreading centers and subduction zones is a known contributor to ocean heat budgets, but typically dispersed over vast areas with minimal impact on surface conditions. What the current data suggests is localized concentration. Thermal energy, possibly from accelerated tectonic activity in the subduction zone beneath the Mariana system, channeling upward through fracture networks in the oceanic crust, creating a heat corridor in the deep ocean that happens to align perfectly with Sinlaku's track. Seismic monitoring stations throughout the Western Pacific have recorded elevated microseismicity along the Mariana Arc over the past 96 hours. Small events, magnitude 3 to 4, occurring at depths consistent with slab deformation in active subduction zones. Individually, none of these events are unusual. The Mariana System is one of the most seismically active regions on Earth. What is unusual is the timing. The cluster of seismic events began approximately 72 hours before Sinlaku started its impossible intensification sequence. The energy release from those small earthquakes measured cumulatively is orders of magnitude below what would be required to influence atmospheric conditions through any direct mechanism. But energy transfer in coupled Earth systems is not always direct. Thermal energy released from tectonic deformation heats surrounding rock. That heat conducts into seawater, infiltrating fractured oceanic crust. That heated seawater rises through convective circulation, eventually mixing with the deeper ocean layers where storm systems can access it. The timeline from seismic energy release to atmospheric availability is measured in days to weeks under normal diffusion conditions, unless the transfer is occurring through channelized pathways, through fracture networks that act as thermal conduits, delivering heat to the surface ocean far faster than diffuse conduction would allow. We are watching a storm follow a line of geothermal discharge with navigational precision that atmospheric steering currents alone cannot explain, and the heat source sustaining it is coming from beneath the ocean floor. Thermodynamics does not care what we believe is possible. Energy cannot be created. It can only transfer from one system to another. When a Category 5 typhoon maintains intensity beyond all observed limits, the energy sustaining it must be coming from somewhere. Calculate Sinlaku's total energy output. Factor in the wind kinetic energy, the latent heat release from condensation, the work being done lifting millions of tons of air through the storm's circulation. The numbers reach into the petajoule range per day. That energy is not appearing from nothing. Standard atmospheric models account for storm energy through ocean heat transfer. Warm surface water evaporates, moisture rises into the storm system, condensation releases latent heat, that heat drives the circulation. In a normal storm, you can trace every joule of energy back to solar heating of the ocean surface. The energy budget balances. Input equals output, within measurement uncertainty. Sinlaku's energy budget does not balance. The output exceeds what solar-heated surface water can provide, even accounting for the anomalously warm sea surface temperatures beneath the storm. Run the calculation carefully. Ocean heat content in the upper 200 meters along Sinlaku's path, integrated over the area the storm has traversed, provides enough energy to sustain a Category 4 system, perhaps reaching Category 5 for brief periods before normal cooling mechanisms engage. It does not provide enough energy to sustain 18 continuous hours of accelerating intensification while simultaneously generating electromagnetic signatures that appear in satellite data. The energy budget has a deficit. Something is supplying additional energy to the system. Geothermal energy flux from active tectonic boundaries is measured in milliwatts per square meter. Averaged over ocean basin scales, it contributes negligibly to surface heat budgets. But those measurements assume diffuse, steady-state heat flow. What if the flow is not steady? What if tectonic stress release during seismic events produces transient pulses of elevated heat flux, concentrated along fracture zones, delivered to the ocean in bursts rather than continuous trickle? Theoretical models for this scenario exist in geophysical literature. They were developed to explain anomalous warming events detected near deep-sea hydrothermal systems. They were never applied to tropical meteorology because the disciplines do not overlap. Apply them now. Model what happens when a storm system crosses a region of pulsed geothermal discharge. The deep ocean warms. Convection carries that heat upward. The storm, which draws energy from the warmest available water, naturally tracks toward the heat source. the storm intensifies. The intensification increases wind-driven ocean mixing, which paradoxically should cool the surface, but instead keeps pulling warmer water from the geothermally heated reservoir below. Positive feedback: the harder the storm works, the more heat it accesses. The system couples, atmospheric geological coupling. Two Earth subsystems, one driven by solar energy, one driven by internal planetary heat, synchronizing their behavior through shared physical processes. The scientific literature contains approximately 47 peer-reviewed papers discussing theoretical mechanisms for such coupling. None were written by meteorologists, none inform operational weather forecasting, and none predicted what we are watching happen in real time over the Western Pacific. Sinlaku is not just a storm anymore. It is a hybrid system, drawing energy from both the atmosphere and the deep Earth, operating in a regime where our separate models for weather and geology no longer apply because the boundaries between them have dissolved. The physics violation is not that this is happening. The physics allows it, barely, under conditions extreme enough that we have never documented them before. The violation is that we built our entire emergency response framework assuming it could not happen, and now it is. 36 hours ago, before any public weather service upgraded Sinlaku to Category 5, before civilian meteorologists began using words like unprecedented in their forecasts, military weather reconnaissance aircraft were quietly diverted from their planned flight paths. Standard protocol for major Western Pacific storms involves direct penetration flights through the eye wall, gathering in situ atmospheric data that satellites cannot provide. These missions are routine. They are announced in advance. Flight tracks are published. Until they are not, check the military weather reconnaissance flight logs for the past 72 hours. Notice what is missing. No WC-13OJ, Hercules penetrations through Sinlaku's core, no drops-on deployments into the eye wall, no direct pressure measurements from the storm's center. Official explanation, when requested through public affairs channels, cited operational scheduling conflicts and aircraft maintenance requirements. 3 separate airframes, all suddenly unavailable for the most significant storm intensification event in modern meteorological history. Probability of coincidence approaches 0. Communication intercepts between Pacific military weather centers and research facilities. Fragments available through open-source intelligence monitoring contain references to contingency frameworks being activated, not standard tropical cyclone protocols, something else. The phrase used in one transmission was compound scenario assessment, terminology that does not appear in any published military weather operation manual. Another fragment mentioned resource pre-positioning timelines that began 72 hours before the Category 5 classification became public knowledge. Someone knew this intensification was coming before the atmospheric models predicted it. Examine the emergency supply movements. 4 days ago, while Sinlaku was still classified as a tropical storm, cargo aircraft began delivering hardened communications equipment and extended duration emergency power systems to military installations across the Western Pacific. Not standard storm preparation. Equipment designed for scenarios where conventional infrastructure fails completely and recovery timelines extend beyond normal disaster response windows. The requisition orders were filed under classified operational codes that prevent external tracking of what specifically was moved and why. Similar patterns appeared before 3 previous storms, the ones that showed impossible brief intensification before sudden collapse. Reconnaissance flights diverted, communication patterns shifted, equipment moved, then the storms weakened, the emergency posture scaled back, and the preparation activities were filed away in operational archives where civilian researchers do not have access. Whatever protocols were activated for those events, they were activated again for Sinlaku, except this time the storm is not collapsing. The contingency frameworks are still running, and the silence from official military weather channels is growing louder. Research facilities that normally publish preliminary findings on unusual atmospheric events have gone quiet. Scientists who typically share data through academic networks have stopped responding to inquiries about Sinlaku's electromagnetic signatures, not because they lack information, because someone told them the information is no longer appropriate for open publication. The boundary between civilian meteorology and classified atmospheric research is normally porous. Data flows both directions. That flow has stopped. The storm everyone can see on satellite imagery is being studied by instruments and analyzed through frameworks that the public will never hear about. And the gap between what is known and what is being said is widening every 6 hours. Go back exactly 10 years. Late September, Western Pacific. Super Typhoon Vongfong intensified from Category 2 to Category 5 in 18 hours, a rate that broke records and produced intensification curves meteorologists described as nearly vertical. Peak sustained winds reached 295 kilometers per hour. Then, without any obvious atmospheric trigger, the storm rapidly weakened. Within 24 hours, it was Category 3. The official explanation cited increasing wind shear and cooler ocean temperatures along the forecast track. Data archives tell a different story. Ocean buoy measurements from beneath Vongfong's path showed no significant cooling during the weakening phase. Wind shear aloft did increase, but not to levels that should have produced such catastrophic intensity loss. What the archived data does show, buried in supplementary research datasets that were never highlighted in official post-storm analyses, are electromagnetic anomalies, 6-hour pulses, exactly matching the signature appearing in Sinlaku's satellite readings. The pulses continued through Vongfong's peak intensity phase. Then they stopped. 90 minutes after the last electromagnetic pulse was recorded, the storm began its rapid weakening sequence. Jump forward 4 years. Hurricane Patricia, Eastern Pacific, October 2015. Fastest intensification ever recorded in the Western Hemisphere. Central pressure dropped from 985 millibars to 872 millibars in 24 hours. Lowest pressure ever measured in any tropical cyclone basin. Peak winds exceeded 370 kilometers per hour in brief bursts. Then, approaching the Mexican coastline, Patricia collapsed. Category 5 to Category 1 in 12 hours. Wind shear was cited. The ocean heat content data showed the same anomaly. No cooling where cooling should have occurred. And deep in the electromagnetic monitoring archives, the same 6-hour pulse signature, active during intensification, ceasing abruptly before the weakening began. 3 more events over the past decade, different ocean basins, different months, different atmospheric steering patterns, all sharing the same profile. Rapid intensification beyond normal limits, sustained peak intensity, while electromagnetic pulses continued. Sudden catastrophic weakening when the pulses stopped. Each event was studied individually, treated as a unique confluence of atmospheric variables. No one connected them because the electromagnetic data exists in research streams that tropical meteorologists do not routinely access. The pattern was there, documented, published in specialized geophysics journals, and completely invisible to the weather forecasting community. Plot those events on a tectonic map. Notice where they occurred, each one positioned over active geological boundaries, subduction zones, volcanic island arcs, regions where deep Earth heat flux exceeds basin-wide averages. The correlation between impossible storm intensification and geologically active ocean floor is statistically undeniable once you see all 6 events together. 6 storms in 10 years, 6 different locations, same electromagnetic signature, same coupled intensification behavior, same abrupt termination when the deep energy source ceased operating. Sinlaku is event number 7, the pattern holds. The electromagnetic pulses are active. The geothermal corridor is channeling heat to the surface ocean. The intensification is accelerating beyond all atmospheric limits. But there is one critical difference. The previous 6 events lasted between 8 and 36 hours before the electromagnetic signature ceased and the storms collapsed. Sinlaku has now sustained this state for 48 hours. The pulses are not stopping. The pattern is not terminating. Whatever mechanism caused the previous events to shut down after brief windows has not activated. The coupled system is still running, and we have no historical precedent for what happens when it does not stop. 72 hours. That is the current forecast window until potential landfall on United States territory. 3 days. Under normal circumstances, 72 hours provides adequate time for evacuation orders, resource staging, and emergency preparations. These are not normal circumstances. Normal circumstances assume the storm approaching your coastline is the same storm forecasters described 3 days ago. Sinlaku will not be the same storm. It is evolving every 6 hours, and each evolution makes the previous forecast obsolete. Current track projections show landfall on Guam, potentially extending to the northern Mariana Islands. Population approximately 170,000. Military installations hosting strategic bomber and submarine assets. Infrastructure designed to withstand Category 4 typhoons based on historical maximum observed wind speeds in the region. None of that infrastructure was designed for 350 km/h sustained winds. At that threshold, we are no longer discussing structural damage tolerances and safety margins. We are discussing physics that building codes never contemplated. Calculate what 350 km/h winds do to a concrete structure. The force on a surface increases with the square of wind velocity. Double the wind speed, quadruple the force. At 350 km/h, wind loading exceeds 25 kilopascals on vertical surfaces. Concrete masonry designed to Category 4 standards begins experiencing tensile failure, not cosmetic damage, structural disintegration at the molecular bond level. Walls do not crack, they atomize, roofs do not lift off, they vaporize into projectile clouds moving at velocities that turn plywood into armor-piercing weapons. Emergency planners use a concept called safe refuge. Designated structures, usually government buildings or military facilities, with hardened construction where populations can shelter when evacuation is impossible. Those designations are based on historical storm intensity data. Guam's designated shelters were validated for sustained winds up to 280 km/h with appropriate safety margins. If Sinlaku arrives at 350 km/h, there are no safe refuges. The structures will fail. Not might fail. Will fail. The mathematics are absolute. The evacuation option is equally impossible. Guam is an island. You cannot drive to higher ground in another state. Air evacuation for 170,000 people requires weeks of sustained airlift operations under perfect weather conditions. The storm will arrive in 72 hours. Naval evacuation is theoretically possible but requires calm seas and available shipping capacity. Sinlaku is already generating 30-foot seas across its outer circulation bands. No civilian vessels are operating in the Western Pacific approach lanes. Military sea lift capability is finite, and much of that capability is already committed to operational taskings that cannot be immediately suspended, so the population will shelter in place, in structures designed for a different category of threat, while a storm that is still intensifying every 6 hours approaches their location. The current forecast has Sinlaku making landfall at peak strength, not post-peak weakening, which is what typically happens as storms approach land and begin interacting with terrain. Peak strength, 350 km/h winds, 40-foot storm surge in confined bays, rainfall rates exceeding 15 centimeters per hour, and underlying all of it, the same seismically active subduction zone that appears to be channeling the energy sustaining the storm's impossible intensification. 72 hours. The countdown is absolute, and every 6-hour intensification pulse that occurs in that window makes the mathematics of survival worse. There is a conversation happening in closed research channels, never appearing in public meteorological discussions, never referenced in official storm briefings, that needs to be said plainly. What if Sinlaku represents something we have never categorized before? Not a hurricane, not a typhoon, not weather in the conventional sense. What if we are watching the first documented case of full atmospheric geological system coupling? The theoretical framework exists. Published research, peer-reviewed and available in academic databases, describes the conditions under which Earth's subsystems can synchronize. Atmosphere and ocean are well understood coupled systems. El Niño demonstrates that coupling on decadal timescales. Ocean and solid Earth couple through tectonic processes that generate seafloor spreading and subduction zone dynamics. These couplings are established science. What has never been documented outside of theoretical models is three-way coupling: atmosphere, ocean, and solid Earth operating as a single integrated system. The mechanism requires specific preconditions: tectonically active region generating elevated geothermal heat flux, ocean basin positioned to concentrate that heat through convective circulation, atmospheric conditions favorable for tropical cyclone development positioned over the geothermal anomaly at the moment when tectonic activity releases a pulse of energy. The probability of all three conditions aligning is vanishingly small, small enough that it should never happen in the observational record, except it has happened 7 times in 10 years, and the 7th event is not terminating the way the previous 6 did. Consider what full system coupling means. The storm draws energy from the ocean. The ocean draws energy from geothermal discharge. The geothermal discharge is driven by tectonic stress release. But the storm, through its circulation, alters ocean mixing patterns, which changes how heat distributes through the water column, which affects pressure loading on the seafloor, which influences stress states in the underlying crust. Feedback. The storm is not just extracting energy from the Earth, it is potentially influencing the rate at which that energy is released. The system is self-regulating, self-amplifying, operating in a regime where the boundaries between atmosphere and geology have dissolved into coupled dynamics. If this hypothesis is correct, Sinlaku is not following atmospheric steering currents toward Guam. It is following the geothermal corridor. The electromagnetic pulses are not coincidental. They are the signature of energy transfer between systems. And the reason the storm has not collapsed, the reason it continues intensifying while every atmospheric model predicts it should be weakening, is because the deep energy source is still operating. The tectonic system beneath the Mariana Trench is still releasing stress, and as long as it continues, the storm will continue accessing that energy regardless of what the atmosphere alone can provide. This is the hypothesis no official source will state, because stating it would require acknowledging that our entire framework for understanding and forecasting tropical cyclones is incomplete. It would require admitting that there are storm categories beyond Category 5, states of atmospheric organization driven by energy sources we do not monitor and cannot predict. It would require fundamentally restructuring how we think about the relationship between weather and the deep Earth, and it would require telling 170,000 people that the storm approaching them is something we have never successfully forecasted before. The mathematics of coupled systems show something else, something that makes the 72-hour countdown even more critical. Coupled systems, once fully synchronized, can exhibit threshold behavior. They remain stable in their coupled state until some critical variable changes, at which point the system rapidly transitions to a different state. For the 6 previous events, that transition was termination. The coupling broke, the electromagnetic pulses ceased, the storms collapsed. But coupled systems theory also allows for a different transition, runaway amplification, where the feedback between systems becomes so strong that the coupling intensifies until some physical limit forces catastrophic system failure. We do not know which transition Sinlaku will undergo. We do not know what determines which pathway a coupled storm follows, and we will not know until it happens. Right now, at this exact instant, Sinlaku's central pressure is 912 millibars and falling. Wind speeds are 335 kilometers per hour and rising. The storm has just completed its 8th consecutive 6-hour intensification pulse. Electromagnetic monitoring satellites detected the signature at exactly 1200 hours UTC, precisely on schedule, precisely matching the pattern that has held for the past 48 hours. The coupled system is still running. 60 hours until potential landfall. Ocean buoys along the forecast track show the thermal corridor is still intact. Deep water temperatures at 400 meters depth are 6 degrees Celsius above seasonal norms. The heat source is not diminishing. Seismic monitoring stations recorded another magnitude 4 event in the Mariana subduction zone 18 minutes ago. The tectonic system is still releasing energy. The fuel supply for the atmospheric geological coupling is still flowing. Military reconnaissance aircraft remain grounded. No direct atmospheric measurements from inside the storm's core. All intensity estimates are derived from satellite interpretation algorithms calibrated on storms that followed normal intensification curves. If those algorithms are underestimating Sinlaku's actual wind speeds, if the coupled system is producing wind velocities higher than satellite signatures suggest, we will not know until ground-based measurements become available, at landfall, when it is too late for the information to matter. Emergency evacuation orders are in effect across Guam and the Northern Marianas. Designated shelters are open. Populations are moving to refuge locations designed for storms that obeyed the rules. The public messaging from official weather services uses language like extremely dangerous and potentially catastrophic, the standard severe warning terminology. It does not use language like unprecedented physics or coupled system dynamics or geothermal energy transfer, because that language would require explanations that official channels are not prepared to provide. The scientific community studying this event in real time is watching measurements accumulate that do not fit existing frameworks. Each 6-hour data cycle brings new readings that push Sinlaku further outside the envelope of observed storm behavior. The electromagnetic pulses continue, the thermal corridor persists, the intensification accelerates. And somewhere in classified research facilities, analysts are running scenarios that will never appear in public forecasts, calculating outcomes for what happens if the coupling does not break, if the storm reaches landfall at full coupled system strength, if the energy reservoir sustaining it has not exhausted itself by the time the eye wall crosses the coastline. 60 hours from now, we will know whether Sinlaku represents a singular anomaly, an edge case in the statistics of extreme weather, or whether it represents the first documented evidence that Earth's systems can couple in ways that produce phenomena we have no framework to predict or control. 60 hours from now, 170,000 people will know whether the shelters they are occupying can withstand forces that were never part of the design calculations. 60 hours from now, the pattern that has held for 7 storms over 10 years will either terminate the way it did for the previous 6, or it will continue into territory that theoretical models allow, but observed reality has never explored. Right now, the instruments are still recording. The electromagnetic pulses are still synchronizing with intensification cycles. The storm is still following the geothermal corridor with navigational precision, and the countdown is still running. 59 hours, 42 minutes until forecast landfall. The numbers are still climbing, the coupling is still holding, and whatever is sustaining this storm against every atmospheric law that should be stopping it is still operating. This is not over, this is accelerating, and we are watching it happen in real time with instruments that can measure everything except what it means.